Welcome to the AGPIAL Audiobook production of Building a Scalable and Secure Multi-VPC AWS Network Infrastructure AWS Whitepaper. Don't forget to like and subscribe. Thank you. Now let's go. Building a Scalable and Secure Multi-VPC AWS Network Infrastructure Abstract. AWS customers often rely on hundreds of accounts and VPCs to segment their workloads and expand their footprint. This level of scale often creates challenges around resource sharing, inter-VPC connectivity, and on-premises to VPC connectivity. This white paper describes best practices for creating scalable and secure network architectures in a large network using AWS services like Amazon VPC, AWS Transit Gateway, AWS PrivateLink, and AWS Direct Connect Gateway. It demonstrates solutions for managing growing infrastructure, ensuring scalability, high availability, and security while keeping overhead costs low. Introduction. AWS customers begin by building resources in a single AWS account that represents a management boundary which segments permissions, costs, and services. However, as the customer's organization grows, greater segmentation of services becomes necessary to monitor costs, control access, and provide easier environmental management. A multi-account solution solves these issues by providing specific accounts for IT services and users within an organization. AWS provides several tools to manage and configure this infrastructure, including AWS Landing Zone and AWS Control Tower. AWS Landing Zone and AWS Control Tower automate the setup and integration of multiple AWS services to provide a baseline, highly controlled, multi-account environment with identity and access management, IAM, governance, data security, network design, and logging. The AWS Landing Zone solution in Figure 1 includes 4 accounts: the AWS Organizations account, used to manage configuration and access to AWS Landing Zone managed accounts; the Shared Services account, used for creating infrastructure shared services such as directory services; the Log Archive account, centralized logging into S3 buckets; and the Security account, to be used by a company's security and compliance team to audit or perform emergency security operations in case of an incident in the spoke accounts. This white paper introduces a network services account owned by the networking team managing your AWS infrastructure. The networking services and the network infrastructure for the account are shared by all the accounts and VPCs in a centralized fashion, similar to a hub-spoke design. This design enables better manageability for your landing zone and helps reduce costs by removing the need to duplicate network services in each spoke VPC and account. Note in this white paper, landing zone is a broad term for the scalable, secure, and performant multi-account/multi-VPC setup where you deploy your workloads. This setup can be built using any tool. Most customers begin with a few VPCs to deploy their infrastructure. The number of VPCs a customer owns is usually related to their number of accounts, users, and staged environments, prod, dev, test, etc. As cloud usage grows, the number of users, business units, applications, and regions that a customer interacts with multiply, leading to the creation of new VPCs. As the number of VPCs grows, cross-VPC management becomes essential for the operation of the customer's cloud network. This white paper covers best practices for 3 specific areas in cross-VPC and hybrid connectivity. Network connectivity, interconnecting VPCs and on-premises networks at scale. Network security, building centralized egress points for accessing the internet and endpoints like NAT Gateway, VPC endpoints, and AWS PrivateLink. DNS management, resolving DNS within the landing zone and hybrid DNS. VPC-to-VPC connectivity. Customers can use 2 different VPC flow patterns to set up multi-VPC environments, many-to-many, or hub and spoke. In the many-to-many approach, the traffic between each VPC is managed individually between each VPC. In the hub and spoke model, all inter-VPC traffic flows through a central resource, which routes traffic based on established rules. VPC peering. The simplest way to connect 2 VPCs is to use VPC peering. In this setup, a connection enables full bidirectional connectivity between the VPCs. This peering connection is used to route traffic between the VPCs. VPCs across accounts and AWS regions can also be peered together. VPC peering only incurs costs for traffic traveling over the connection. There is no hourly infrastructure fee. VPC peering is point-to-point connectivity, and it does not support transitive routing. For example, if you have a VPC peering connection between VPC A and VPC B and between VPC A and VPC C, an instance in VPC B cannot transit through VPC A to reach VPC C. To route packets between VPC B and VPC C, you are required to create a direct VPC peering connection. At scale, when you have tens hundreds of VPCs, interconnecting them with peering results in a mesh of thousands of peering connections, which are difficult to manage and scale. There is a maximum limit of 125 peering connections per VPC. Figure 2, Network setup using VPC peering. If you are using VPC peering, on-premises connectivity, VPN and/or direct connect, must be made to each VPC. Resources in a VPC cannot reach on-premises using the hybrid connectivity of a peered VPC. Figure 2. VPC peering is best used when resources in one VPC must communicate with resources in another VPC. The environment of both VPCs is controlled and secured, and the number of VPCs to be connected is less than 10, to allow for the individual management of each connection. VPC peering offers the lowest overall cost when compared to other options for inter-VPC connectivity. Transit VPC Solution. Transit VPCs can solve some of the shortcomings of VPC peering by introducing a hub-and-spoke design for inter-VPC connectivity. In a transit VPC network, one central VPC, the hub VPC, connects with every other VPC, spoke VPC, through a VPN connection typically leveraging BGP over IPsec. The central VPC contains EC2 instances running software appliances that route incoming traffic to their destinations using the VPN overlay. Figure 3. Transit VPC peering has the following advantages. Transitive routing is enabled using the overlay VPN network, allowing for a simpler hub-and-spoke design. When using third-party vendor software on the EC2 instance in the hub transit VPC, vendor functionality around advanced security, Layer 7 firewall/IPS/IDS, can be leveraged. If customers are using the same software on premises, they benefit from a unified operational/monitoring experience. Transit VPC comes with its own challenges, such as higher costs for running virtual appliances, limited throughput per VPC, up to 1.25 gigabits per second per VPN tunnel, and additional configuration and management overhead. Customers have to manage the availability and redundancy of EC2 instances. Transit Gateway. AWS Transit Gateway provides a hub-and-spoke design for connecting VPCs and on-premises networks as a fully managed service without requiring you to provision virtual appliances like the Cisco CSRs. No VPN overlay is required, and AWS manages high availability and scalability. Transit Gateway enables customers to connect thousands of VPCs. You can attach all your hybrid connectivity, VPN and direct connect connections, to a single transit gateway, consolidating and controlling your organization's entire AWS routing configuration in one place. Figure 4. Transit Gateway controls how traffic is routed among all the connected spoke networks using route tables. This hub-and-spoke model simplifies management and reduces operational cost because VPCs only connect to the Transit Gateway to gain access to the connected networks. Transit Gateway is a regional resource and can connect thousands of VPCs within the same AWS region. You can create multiple transit gateways per region, but transit gateways within an AWS region cannot be peered, and you can connect to a maximum of 3 transit gateways over a single direct connect connection for hybrid connectivity. For these reasons, you should restrict your architecture to just one transit gateway connecting all your VPCs in a given region, and use transit gateway routing tables to isolate them wherever needed. There is a valid case for creating multiple transit gateways purely to limit misconfiguration blast radius. Place your organization's transit gateway in its network services account. This enables centralized management by network engineers who manage the network services account. Use AWS Resource Access Manager, RAM, to share a transit gateway for connecting VPCs across multiple accounts in your AWS organization within the same region. AWS RAM enables you to easily and securely share AWS resources with any AWS account, or within your AWS organization. For more information, refer to the Automating AWS Transit Gateway attachments to a Transit Gateway in a Central Account blog post. Transit Gateway versus Transit VPC. Transit Gateway provides a number of advantages over Transit VPC. Transit Gateway abstracts away the complexity of maintaining VPN connections with hundreds of VPCs. Transit Gateway removes the need to manage and scale EC2-based software appliances. AWS is responsible for managing all resources needed to route traffic. Transit Gateway removes the need to manage high availability by providing a highly available and redundant multi-OS infrastructure. Transit Gateway improves bandwidth for inter-VPC communication to burst speeds of 50 gigabits per second per OS. Transit Gateway streamlines user costs to a simple per hour per /GB transferred model. Transit Gateway decreases latency by removing EC2 proxies and the need for VPN encapsulation. Transit Gateway versus VPC peering. Transit Gateway solves the complexity involved with creating and managing multiple VPC peering connections at scale. While this makes TGW a good default for most network architectures, VPC peering is still a valid choice due to the following advantages it has over TGW. Lower cost. With VPC peering you only pay for data transfer charges. Transit Gateway has an hourly charge per attachment in addition to the data transfer fees. No bandwidth limits. With Transit Gateway, maximum bandwidth, burst, per VPC connection is 50 gigabits per second. VPC peering has no aggregate bandwidth. Individual instance network performance limits and flow limits, 10 gigabits per second within a placement group and 5 gigabits per second otherwise, apply to both options. Only VPC peering supports placement groups. Latency. Unlike VPC peering, Transit Gateway is an additional hop between VPCs. Security groups compatibility. Security groups referencing works with intra-region VPC peering. It does not currently work with Transit Gateway. Within your landing zone setup, VPC peering can be used in combination with the hub and spoke model enabled by Transit Gateway. AWS PrivateLink. Customers may want to privately expose a service/application residing in one VPC, service provider, to other consumer VPCs within an AWS region in a way that only consumer VPCs initiate connections to the service provider VPC. An example of this is the ability for your private applications to access service provider APIs. To use AWS PrivateLink, create a network load balancer for your application in your VPC, and create a VPC endpoint service configuration pointing to that load balancer. A service consumer then creates an interface endpoint to your service. This creates an elastic network interface in your subnet with a private IP address that serves as an entry point for traffic destined to the service. The consumer and service are not required to be in the same VPC. If the VPC is different, the consumer and service provider VPCs can have overlapping IP address ranges. In addition to creating the interface VPC endpoint to access services in other VPCs, you can create interface VPC endpoints to privately access supported AWS services through AWS PrivateLink, Figure 5. The choice between Transit Gateway, VPC peering, and AWS PrivateLink is dependent on connectivity. AWS PrivateLink. Use AWS PrivateLink when you have a client/server set up where you want to allow one or more consumer VPCs unidirectional access to a specific service or set of instances in the service provider VPC. Only the clients in the consumer VPC can initiate a connection to the service in the service provider VPC. This is also a good option when client and servers in the two VPCs have overlapping IP addresses, as AWS PrivateLink leverages ANIs within the client VPC such that there are no IP conflicts with the service provider. You can access AWS PrivateLink endpoints over VPC peering, VPN, and AWS Direct Connect. VPC peering and Transit Gateway. Use VPC peering and Transit Gateway when you want to enable Layer 3 IP connectivity between VPCs. Your architecture will contain a mix of these technologies in order to fulfill different use cases. All of these services can be combined and operated with each other. For example, AWS PrivateLink handling API-style client-server connectivity, VPC peering for handling direct connectivity requirements where placement groups may still be desired within the region or inter-region connectivity as needed, and Transit Gateway to simplify connectivity of VPCs at scale as well as edge consolidation for hybrid connectivity. Amazon VPC Sharing. Sharing VPCs is useful when network isolation between teams does not need to be strictly managed by the VPC owner, but the account-level users and permissions must be. With shared VPC, multiple AWS accounts create their application resources, such as Amazon EC2 instances, in shared, centrally managed Amazon VPCs. In this model, the account that owns the VPC owner shares one or more subnets with other accounts, participants. After a subnet is shared, the participants can view, create, modify, and delete their application resources in the subnets shared with them. Participants cannot view, modify, or delete resources that belong to other participants or the VPC owner. Security between resources in shared VPCs is managed using security groups and subnet network ACLs. VPC sharing benefits. Simplified design, no complexity around inter-VPC connectivity. Fewer managed VPCs. Segregation of duties between network teams and application owners. Better IP4 address utilization. Lower costs, no data transfer charges between instances belonging to different accounts within the same availability zone. Note, when you share a subnet with multiple accounts, your participants should have some level of cooperation since they're sharing IP space and network resources. If necessary, you can choose to share a different subnet for each participant account. One subnet per participant enables network ACL to provide network isolation in addition to security groups. Most customer architectures will contain multiple VPCs, many of which will be shared with 2 or more accounts. Transit Gateway and VPC peering can be used to connect the shared VPCs. For example, let's say you have 10 applications. Each application requires its own AWS account. The apps can be categorized into 2 application portfolios. Apps within the same portfolio have similar networking requirements, App 1 to 5 in marketing and App 6 to 10 in sales. You can have 1 VPC per application portfolio, 2 VPCs total, and the VPC is shared with the different application owner accounts within that portfolio. App owners deploy apps into their respective shared VPC, in this case, in the different subnets for network route segmentation and isolation using NACLs. The 2 shared VPCs are connected via the Transit Gateway. With this setup, you could go from having to connect 10 VPCs to just 2, Figure 6. Hybrid connectivity. This section focuses on securely connecting your cloud resources with your on-premises data centers. There are 2 approaches for enabling hybrid connectivity. 1. One-to-one connectivity. In this setup, a VPN connection and/or Direct Connect private VPC is created for every VPC. This is accomplished by leveraging the Virtual Private Gateway, VGW. This option is great for small numbers of VPCs, but as a customer scales their VPCs, managing hybrid connectivity per VPC can become difficult. 2. Edge consolidation. In this setup, customers consolidate hybrid IT connectivity for multiple VPCs at a single endpoint. All the VPCs share these hybrid connections. This is accomplished by leveraging AWS Transit Gateway and the Direct Connect Gateway. VPN. There are 3 ways to set up VPN to AWS. 1. Consolidate VPN connectivity on Transit Gateway. This option leverages the Transit Gateway VPN attachment on Transit Gateway. Transit Gateway supports IPsec termination for site-to-site VPN. Customers can create VPN tunnels to the Transit Gateway, and can access the VPCs attached to it. Transit Gateway supports both static and BGP-based dynamic VPN connections. Transit Gateway also supports equal cost multipath, ECMP, on VPN attachments. Each VPN connection has a maximum of 1.25 Gbps throughput, and enabling ECMP allows you to aggregate throughput across VPN connections. In this option, you pay for Transit Gateway pricing as well as AWS VPN pricing. We recommended using this option for VPN connectivity. For more information, consult the AWS VPN overview. 2. Terminate VPN on EC2 instance. This option is leveraged by customers in edge cases when they want a particular vendor software feature set, like Cisco DMVPN or GRE, or they want operational consistency across various VPN deployments. You can leverage the Transit VPC design for edge consolidation, but it is important to remember that all the key considerations from the VPC-to-VPC connectivity section for Transit VPC are applicable to hybrid VPN connectivity. You are responsible for managing high availability, and you pay for EC2 instance costs as well as any vendor software licensing. 3. Terminate VPN on a virtual private gateway, VGW. This option enables a one-to-one connectivity design where you create one VPN connection, consisting of a pair of redundant VPN tunnels, per VPC. This is a great way to get started with VPN connectivity into AWS, but as you scale the number of VPCs, edge consolidation design leveraging Transit Gateway will eventually be a better option. VPN throughput to a VPC is limited to 1.25 gigabits per second and ECMP load balancing is not supported. From a pricing perspective, you only pay for AWS VPN pricing, there is no charge for running a VGW. For more information see, AWS VPN pricing and AWS VPN on Virtual Private Gateway. Direct Connect. While VPN over Internet is a great option to get started, Internet connectivity may not be reliable for production traffic. Because of this unreliability, many customers choose AWS Direct Connect, which enables consistent, low latency, high bandwidth dedicated fiber connectivity between customers' data centers and AWS. There are 4 ways to leverage AWS Direct Connect to connect to VPCs. Create a private virtual interface, VIF, to a VGW attached to a VPC. You can create 50 VIFs per Direct Connect connection, enabling you to connect to a maximum of 50 VPCs. One VIF provides connectivity to one VPC. There is one BGP peering per VPC. Connectivity in this setup is restricted to the AWS region that the Direct Connect location is home to. The one-to-one mapping of VIF to VPC, and lack of global access, makes this the least preferred way to access VPCs in the landing zone. Create a private VIF to a Direct Connect gateway associated with multiple VGWs. Each VGW is attached to a VPC. A Direct Connect gateway can connect to up to 10 VGWs globally, except China, in any AWS account. This is a great option if a landing zone consists of a small number of VPCs, 10 or fewer VPCs, and/or you need global access. There is one BGP peering per Direct Connect gateway per Direct Connect connection. Direct Connect gateway is only for north/south traffic flow and does not permit VPC to VPC connectivity. Create a Transit VIF to a Direct Connect gateway associated with Transit Gateway. You can associate a Transit Gateway to a Direct Connect gateway over a dedicated or hosted Direct Connect connection running at 1 gigabit per second or more. This option allows you to connect your on-premises data center to up to 3 Transit Gateways, which can connect to thousands of VPCs, across different AWS regions and AWS accounts over one VIF and BGP peering. This is the simplest setup among the 4 options for connecting multiple VPCs at scale, but you should be mindful of the Transit Gateway limitations. One key limit is that you can advertise only 20 CIDR ranges from a Transit Gateway to on-premises router over the Transit VIF. With option 1 and 2, you pay for Direct Connect pricing. For option 3, you also pay for the Transit Gateway attachment and data transfer charges. Visit the Transit Gateway Associations on Direct Connect documentation for more information. Create a VPN connection to Transit Gateway over Direct Connect Public VIF. A public virtual interface allows you to access all AWS public services and endpoints using the public IP addresses. When you create a VPN attachment on a Transit Gateway, you get 2 public IP addresses for VPN termination at the AWS end. These public IPs are reachable over the public VIF. You can create as many VPN connections to as many Transit Gateways as you want over public VIF. When you create a BGP peering over the public VIF, AWS advertises the entire AWS public IP range to your router. In order to ensure that you only permit certain traffic, for example, allowing traffic only to the VPN termination endpoints, you are advised to use a firewall on premises. This option can be used to encrypt your Direct Connect at the network layer. While the third option, Transit VIF to Direct Connect Gateway, might appear to be the best option because that it lets you consolidate all your on-premises connectivity for a given AWS region at a single point, Transit gateway, using a single BGP session per direct connect connection. Given some of the limits and considerations around option 3, we expect customers to leverage both option 2 and option 3 for their landing zone connectivity requirements. Figure 9 illustrates a sample setup where transit VPC is used as a default method for connecting to VPCs, and a private VPC is used for an edge use case where huge amount of data must be transferred from an on-premises DC to the media VPC. Private VPC is used to avoid transit gateway data transfer charges. As a best practice, you should have at least 2 connections at 2 different direct connect locations for maximum redundancy, a total of 4 connections. You create 1 VPC per connection for a total of 4 private VPCs and 4 transit VPCs. You also create a VPN as a backup connectivity to AWS Direct Connect connections. Use the Network Services account for creating Direct Connect resources, enabling demarcation of network administrative boundaries. Direct Connect connection, Direct Connect gateway and transit gateway can all reside in a Network Services account. In order to share the AWS Direct Connect connectivity with your landing zone, simply share the transit gateway through RAM with other accounts. Centralized egress to Internet. As you deploy applications in your landing zone, many apps will require outbound-only Internet access, for example, downloading libraries/patches/OS updates. You can achieve this preferably by using a Network Address Translation (NAT) gateway, or alternatively an EC2 instance, configured with source NAT/SNAT, as the next hop for all egress Internet access. Internal applications reside in private subnets, while NAT gateway EC2 NAT instances reside in a public subnet. Using the NAT gateway, deploying a NAT gateway in every spoke VPC can become expensive because you pay an hourly charge for every NAT gateway you deploy. See Amazon VPC pricing, so centralizing it could be a viable option. To centralize, we create an egress VPC in the Network Services account and route all egress traffic from the spoke VPCs via a NAT gateway sitting in this VPC leveraging transit gateway, shown in Figure 10. Note, when you centralize NAT gateway using transit gateway, you pay an extra transit gateway data processing charge, compared to the decentralized approach of running a NAT gateway in every VPC. In some edge cases, when you send huge amounts of data through NAT gateway from a VPC, keeping the NAT local in the VPC to avoid the transit gateway data processing charge might be a more cost-effective option. Figure 11, centralized NAT gateway using transit gateway, route table design. In this setup, spoke VPC attachments are associated with route table 1, RT1, and are propagated to route table 2, RT2. We have explicitly added a black hole route to disallow the 2 VPCs from communicating with each other. If you want to allow inter-VPC communication, you can remove the 10.0.0.08 greater than black hole route entry from RT1. This allows them to communicate via the NAT gateway. You can also propagate the spoke VPC attachments to RT1, or alternatively, you can use one route table and associate/propagate everything to that, enabling direct traffic flow between the VPCs using transit gateway. We add a static route in RT1 pointing all traffic to egress VPC. Because of this static route, transit gateway sends all internet traffic through its ANIs in the egress VPC. Once in the egress VPC, traffic follows the rules defined in the subnet route table where these transit gateway ANIs are present. We add a route in this subnet route table pointing all traffic towards NAT gateway. The NAT gateway subnet route table has Internet Gateway, IGW, as the next hop. In order for return traffic to flow back, you must add a static route table entry in the NAT gateway subnet route table pointing all spoke VPC bound traffic to transit gateway as next hop. High availability. For high availability, you should use 2 NAT gateways, one in each OS. Within an OS, the NAT gateway has an availability SLA of 99.9%. Redundancy against component failure within an OS is handled by AWS under the SLA agreement. Traffic is dropped during the 0.1% time when the NAT gateway may be unavailable in an OS. If one OS entirely fails, the transit gateway endpoint along with NAT gateway in that OS will fail, and all traffic will flow via the transit gateway and NAT gateway endpoints in the other OS. Security. You rely on security groups on the source instances, black hole routes in the transit gateway route tables, and the network ACL of the subnet in which NAT gateway is located. Scalability: a NAT gateway can support up to 55,000 simultaneous connections to each unique destination. From a throughput standpoint, you are limited by the performance limits of NAT gateway. Transit gateway is not a load balancer and will not distribute your traffic evenly across NAT gateway in the multiple OSs. The traffic across the transit gateway will stay within an OS, if possible. If the EC2 instance initiating traffic is in AZ1, traffic will flow out of the transit gateway elastic network interface in the same AZ1 in the egress VPC and will flow to the next hop based on that subnet route table that elastic network interface resides in. For a complete list of rules, see NAT gateway rules and limits. For more information, refer to the Creating a Single Internet Exit Point from Multiple VPCs Using AWS Transit Gateway blog post. Using an EC2 instance for centralized outbound using a software-based firewall appliance, on EC2, from AWS Marketplace as an egress point is similar to the NAT gateway setup. This option can be used if you want to leverage the Layer 7 firewall/intrusion prevention/detection system, IPS/IDS, capabilities of the various vendor offerings. In Figure 12, we replace NAT gateway with an EC2 instance, with SNAT enabled on EC2 instance. There are few key considerations with this option. High availability in this setup. You are responsible for monitoring the EC2 instance, detecting failure, and replacing the EC2 instance with a backup/standby instance. Most AWS vendors have automation pre-built for their software deployed in this setup. That automation can control the following: detect failure of the primary EC2-1 instance. Change the route table EGX1 to point all traffic to the backup EC2-2 instance on the failure of primary instance. This must also be done for the subnets in the AZ2. Scalability: transit gateway is not a load balancer and will not distribute your traffic evenly across instances in the two OSs. The traffic across the transit gateway will stay within an OS, if possible. You are limited by the bandwidth capabilities of a single EC2 instance. You can vertically scale this EC2 instance as usage increases. If the vendor you choose for egress traffic inspection doesn't support automation for failure detection, or if you need horizontal scaling, you can use an alternative design. In this design, Figure 13, we don't create a VPC attachment on the transit gateway for egress VPC. Instead, we create an IPsec VPN attachment and create an IPsec VPN from transit gateway to the EC2 instances leveraging BGP to exchanges routes. Advantages: failure detection and rerouting of traffic handled by BGP. No VPC subnet route table automation is required. BGP ECMP can be used to load balance traffic across multiple EC2 instances. Horizontal scaling is possible. Key considerations: VPN management overhead on EC2 instances. Bandwidth at transit gateway is limited to 1.25 gigabits per second per VPN tunnel. With ECMP, transit gateway can support up to 50 gigabits per second total VPN bandwidth. VPN and packet processing capabilities of vendor appliance can be a limiting factor. This design assumes that the FWEC2 instance is operating with the same elastic network interface for inbound and outbound traffic. If you enable ECMP load balancing of traffic across multiple EC2 instances, you must SNAT traffic on the EC2 instance in order to guarantee return flow symmetry, which means the destination won't know the true source. Centralized network security for VPC-to-VPC and on-premises to VPC traffic. AWS provides security groups and subnet NACLs to implement network security within your landing zone. These are Layer 4 firewalls. There may be scenarios where a customer wants to implement a Layer 7 firewall/IPS/IDS within their landing zone to inspect traffic flowing between VPCs or between an on-premises data center and a VPC. This can be achieved using transit gateway and third-party software appliances running on EC2 instances. Using the architecture in Figure 14, we can enable VPC to VPC and on-premises to VPC traffic to flow via the EC2 instances. The setup is similar to what we have already discussed in Figure 12, but additionally we remove the black hole route in Route Table 1 to allow in-turn VPC traffic flow and attach the VPN attachment and/or Direct Connect GW attachment to Route Table 1 to allow hybrid traffic flow. This enables all traffic coming from the spokes to flow to the egress VPC before being sent to the destination. You need static routes in the egress VPC subnet route table, where the firewall EC2 appliances reside, for sending traffic destined to spoke VPCs and on-premises CIDR through transit gateway after traffic inspection. Note: route information is not dynamically propagated from transit gateway into the subnet route table and must be statically entered. There is a soft limit of 50 static routes on a subnet route table. Key considerations when sending traffic to EC2 instances for inline inspection. Additional transit gateway data processing charges. Traffic must go through 2 additional hops, EC2 instance and transit gateway, potential for bandwidth and performance bottlenecks. Additional complexity of maintaining, managing, and scaling EC2 instances. Detecting failure and failing over to standby. Tracking usage and horizontal/vertical scaling. Firewall configuration, patch management. Source network address translation, SNAT, of traffic. When load balancing to guarantee symmetric flow, you should be selective in what traffic passes via these EC2 instances. One way to proceed is to define security zones and inspect traffic between untrusted zones. An untrusted zone can be a remote site managed by a third party, a vendor VPC you don't control/trust, or a sandbox/dev VPC, which has more relaxed security framework compared to rest of your environment. Figure 15 enables direct traffic flow between trusted networks while inspecting traffic flow to/ from untrusted networks using inline EC2 instances. We created 3 zones in this example. Untrusted zone: this is for any traffic coming from the VPN to remote untrusted site or the third-party vendor VPC. Prod zone: this contains traffic from the production VPC and on-premises customer DC. Dev zone: this contains traffic from the 2 development VPCs. The following are sample rules we define for communication across zones. 1. Untrusted zone. Prod zone: communication not allowed to. Prod zone. Dev zone: communication allowed via EC2 FW appliances in egress VPC 3. Untrusted zone. Dev zone: communication allowed via EC2 FW appliances in egress VPC 4. Prod zone and dev zone. Dev zone: direct communication via transit gateway. This is a setup, has 3 security zones, but you might have more. You can use multiple route tables and black hole routes to achieve security isolation and optimal traffic flow. Choosing the right zones is dependent on your overall landing zone design strategy, account structure, VPC design. You can have zones to enable isolation between BU, applications, environments, etc. In this example, we terminate the untrusted remote VPN on transit gateway and send all traffic to software FW appliances on EC2 for inspection. Alternatively, you can terminate these VPNs directly on the EC2 instances instead of transit gateway. With this approach, the untrusted VPN traffic never directly interacts with transit gateway. The number of hops in the traffic flow reduces by 1, and you save on AWS VPN costs. To enable dynamic route exchanges, for transit gateway to learn the CIDR of the remote VPN via BGP, the firewall instances should be connected to transit gateway via VPN. In the native TGW attachment model, you must add static routes in the TGW route table for VPN side, with the next hop as the egress/security VPC. In our setup, figure 15, we have a default route to egress VPC for all traffic, so we don't have to explicitly add any specific static routes. With this approach, you move away from a fully managed transit gateway VPN termination endpoint to a self-managed EC2 instance, adding VPN management overhead as well as additional load on the EC2 instance in terms of compute and memory. Figure 15, traffic isolation using transit gateway and defining security zones. DNS. When you launch an instance into a non-default VPC, AWS provides the instance with a private DNS hostname, and potentially a public DNS hostname, depending on the DNS attributes you specify for the VPC and if your instance has a public IP4 address. When the enabled DNS support attribute is set to true, you get a DNS resolution within the VPC from Route 53 resolver, plus 2 IP offset to the VPC CIDR. By default, Route 53 resolver answers DNS queries for VPC domain names such as domain names for EC2 instances or elastic load balancing load balancers. With VPC peering, Hosts in one VPC can resolve public DNS hostnames to private IP addresses for instances in peered VPCs, provided the option to do so is enabled. The same is applicable for VPCs connected via AWS Transit Gateway. For more information, see Enabling DNS resolution support for a VPC peering connection. If you want to map your instances to a custom domain name, you can use Amazon Route 53 to create a custom DNS to IP mapping record. An Amazon Route 53 hosted zone is a container that holds information about how you want Amazon Route 53 to respond to DNS queries for a domain and its subdomains. Public hosted zones contain DNS information that is resolvable over the public internet, while private hosted zones are a specific implementation that only presents information to VPCs that have been attached to the specific private hosted zone. In a landing zone setup where you have multiple VPCs/accounts, you can associate a single private hosted zone with multiple VPCs across AWS accounts and across regions. The end hosts in the VPCs use their respective Route 53 resolver IP. +2 offset the VPC CIDR, as the name server for DNS queries. The Route 53 resolver in VPC accepts DNS queries only from resources within a VPC. Hybrid DNS. Coordinating DNS resolution between AWS landing zone setup and on-premises resources is one of the most critical pieces in a hybrid network. Customers implementing hybrid environments usually have a DNS resolution system already in place, and they want a DNS solution that works in tandem with their current system. When you integrate DNS for the VPCs in an AWS region with DNS for your network, you need a Route 53 resolver inbound endpoint for DNS queries that you're forwarding to your VPCs, and a Route 53 resolver outbound endpoint for queries that you're forwarding from your VPCs to your network. As shown in Figure 16, you can configure outbound resolver endpoints to forward queries it receives from EC2 instances in your VPCs to DNS servers on your network. To forward selected queries from a VPC to on-premises, create Route 53 resolver rules that specify the domain names for the DNS queries that you want to forward, such as example.com, and the IP addresses of the DNS resolvers on your network where you want to forward the queries. For inbound queries from on-premises to Route 53 hosted zones, DNS servers on your network can forward queries to inbound resolver endpoints in a specified VPC. This allows your on-premises DNS resolvers to easily resolve domain names for AWS resources, such as EC2 instances or records in a Route 53 private hosted zone associated with that VPC. It is not recommended to create Route 53 resolver endpoints in every VPC of the landing zone. Centralize them in a central egress VPC, in the network services account. This approach allows for better manageability while keeping the costs low. You are charged an hourly fee for each inbound/outbound endpoint you create. You share the centralized inbound and outbound endpoint with the rest of the landing zone. Outbound resolution. Use the network services account to write resolver rules, based on which DNS queries will be forwarded to on-premises DNS servers. Using Resource Access Manager, RAM, share these Route 53 resolver rules with multiple accounts, and associate with VPCs in the accounts. EC2 instances in Spoke VPCs can send DNS queries to Route 53 resolver, and Route 53 resolver service will forward these queries to on-premises DNS server via the outbound Route 53 resolver endpoints in the egress VPC. You don't need to peer Spoke VPCs to the egress VPC, or connect them via Transit Gateway. Do not use the IP of the outbound resolver endpoint as the primary DNS in the Spoke VPCs. Spoke VPCs should use Route 53 resolver to offset of the VPC CIDR in their VPC. Figure 17, centralizing Route 53 resolver endpoints in egress VPC inbound DNS resolution. Create Route 53 resolver inbound endpoints in a centralized VPC and associate all the private hosted zones in your landing zone with this centralized VPC. For more information, see associating more VPCs with a private hosted zone. Multiple private hosted zones, PHZ, associated with a VPC cannot overlap. As shown in Figure 17, this association of PHZ with the centralized VPC will enable on-premises servers to resolve DNS for any entry in any private hosted zone, associated with central VPC, using the inbound endpoint in the centralized VPC. For further more information on hybrid DNS setups, See Centralized DNS Management of Hybrid Cloud with Amazon Route 53 and AWS Transit Gateway and Hybrid Cloud DNS options for Amazon VPC. Centralized access to VPC private endpoints. A VPC endpoint allows you to privately connect your VPC to supported AWS services without requiring an internet gateway or a NAT device. Instances in your VPC do not require public IP addresses to communicate with AWS service endpoints with this interface endpoint. Traffic between your VPC and other services does not leave the AWS network backbone. Two types of endpoints can currently be provisioned: interface endpoints, powered by AWS PrivateLink, and gateway endpoints. Gateway endpoints are free to provision, and there is not a strong use case for centralization. Interface VPC endpoints. An interface endpoint consists of one or more elastic network interfaces with a private IP address that serves as an entry point for traffic destined to a supported AWS service. When you provision an interface endpoint, a cost is incurred by users for every hour the endpoint is running. By default, you create an interface endpoint in every VPC from which you want to access the AWS service. This can be expensive and difficult to manage in the landing zone setup where a customer wants to interact with a specific AWS service across multiple VPCs. To avoid this, you can host the interface endpoints in one centralized VPC. All the spoke VPCs will use these centralized endpoints. When you create a VPC endpoint to an AWS service, you can enable private DNS. When enabled, the setting creates an AWS Managed Route 53 Private Hosted Zone, PHC, which enables the resolution of public AWS service endpoint to the private IP of the interface endpoint. The managed PHC only works within the VPC with the interface endpoint. In our setup, when we want spoke VPCs to be able to resolve VPC endpoint DNS hosted in a centralized VPC, the managed PHC won't work. To overcome this, disable the option that automatically creates the private DNS when an interface endpoint is created. Alternatively, you can manually create a Route 53 PHC and add alias record with the full AWS service endpoint name pointing to the interface endpoint as shown in Figure 18. We associate this private hosted zone with other VPCs within the landing zone. This configuration allows the spoke VPCs to resolve the full service endpoint names to interface endpoints in the centralized VPC. Note: to access the shared private hosted zone, the hosts in the spoke VPCs should use the Route 53 resolver IP of their VPC. Interface endpoints are also accessible from on-premises networks over VPN and Direct Connect. Use conditional forwarding rules to send all DNS traffic for the full service endpoint names to Route 53 resolver inbound endpoints, which will resolve DNS requests according to the private hosted zone. In Figure 19, Transit Gateway enables traffic flow from the spoke VPCs to the centralized interface endpoints. Create VPC endpoints and the private hosted zone for it in Network Services account and share it with spoke VPCs in the spoke accounts. For more details on sharing endpoint information with other VPCs, refer to the Integrating AWS Transit Gateway with AWS PrivateLink and Amazon Route 53 Resolver blog post. Note: a distributed VPC endpoint approach, that is, an endpoint per VPC, allows you to apply least privilege policies on VPC endpoints. In a centralized approach, you will apply and manage policies for all spoke VPC access on a single endpoint. With growing number of VPCs, the complexity of maintaining least privilege with a single policy document might grow. Single policy document also results in larger blast radius. You are also restricted on the size of the policy document, 20,480 characters. Conclusion: as you scale your usage of AWS and deploy applications in the AWS landing zone, the number of VPCs and networking components increases. This white paper explained how we can manage this growing infrastructure, ensuring scalability, high availability, and security while keeping costs low. Making the right design decisions when leveraging services like Transit Gateway, Shared VPC, AWS Direct Connect, VPC endpoints, and third-party software appliances becomes critical. It is important to understand the key considerations of each approach and work backwards from your requirements and analyze as to which option or combination of options fit you best. Contributors: the following individuals contributed to this document: Siddhartha Chauhan, Solutions Architect; Amazon Web Services Amir Abu Akil, Cloud Infrastructure Architect, Amazon Web Services. Sohaib Tahir, Solutions Architect, Amazon Web Services. This has been an AGPIAL audiobook. A good person is always learning. Don't forget to like and subscribe. Thanks for listening. Check out our other channel Conant. Have a great day and enjoy life.